Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll get started with Logistic Regression, Chapter 11, and the notes are there. So we saw logistic regression briefly last semester in ADA1 when we fit a binary response variable to a continuous X predictor variable to see if there was a relationship. And we got those sigmoidal curves. Just as a quick reminder, if I jump to the last page of this, we had this sort of S-shaped curve when we were modeling the probability of an event happening or not happening. And more generally, logistic regression is used to predict an outcome of a categorical dependent variable based on one or more predictor variables. And we want to model the probability that a certain outcome is realized as a function of these explanatory or predictor variables. So that it's called logistic regression because we use a logistic function to map the probability to the explanatory variables. Logistic regression is frequently used to refer to a problem when we only have a binary response, sort of true-false, that Boolean type response. Heads, tails in a coin flip, success, failure more generally. But you can deal with problems that have more than two categories. It's called multinomial logistic regression instead of binomial logistic regression. And there's even special cases where you might have ordered categories. A case of a set of ordered response variables might be something like a Likert scale, where you have strongly disagree, disagree, neutral, agree, strongly agree. Those are 5 categories, and there's a probability of a response following in each of those categories, but they also have an ordered structure. So logistic regression measures that relationship between that categorical dependent variable and possibly several continuous variables, just as any multiple regression problem. And we need a way to relate those binary outcomes, success, failure, to a probability. And that is going to be the main focus of this video for this chapter. So that brings us to generalized linear models. So generalized linear model is different from a general linear model. We've already been working basically with a general linear model framework when we do multiple regression. And that assumes that we've got normal residuals. So basically that some function of the response is normally or normally distributed. Generalized linear models, or GLM, gives us a way to specify a response variable that is different than having a normal distribution. Such a model is specified by what's called a link function. Here we go. A link function, which links the some characteristic of the response variable to the outcomes we observe relative to the predictor variables. All right, all this will become a bit clearer in a second. In R, we've been using a function LM, and now we can use a function GLM, which is for generalized linear model. It has this structure. It has a formula, the way we've had a formula before, basically y tilde and then the set of x variables, and the data, and that's all we really needed in the linear model function. In the linear model function, we also have weights and subset. But what's special here is the family. That's the key parameter. It's a way of specifying what we think what distribution we're modeling with the response variable. So I've got a little table here where we can specify that family variable to. So if we want to do a standard general linear model, not generalized, but general linear model, then we can do a Gaussian here, and in which case we would probably just use the function LM rather than GLM, but it allows you to do a Gaussian distribution. In our case, in this chapter, we are going to use binomial as the family, and that means that there's going to be a binomial variance component rather than normal. So, by the way, this word Gaussian is the same as normal distribution. And for the binomial logistic regression, we actually have three choices of a link function, and the subtleties here I'm not going to delve into. We will typically just use the Logit link function, but there are two other versions. There's something called the probit, which is based on normality, and there's something called the complementary log-log link function as well. But there's other families too. There's a Poisson family, which is helpful for when you're modeling counts. So, how many spots does a ladybug have? 0, 1, 2, 3, up to infinity, theoretically, at least for the model sake. Or how many cracks in each square of a piece of sidewalk. Those things tend to follow the Poisson distribution. Gamma distribution allows for a continuous response, but has a bit of right skewness to it. We can do inverse Gaussian, and then you could also define your own. But we're going to stick, for this chapter, we're looking at this row for the binary logistic regression. All right, so when we specify the general linear model, we'll specify our formula, like y tilde x. Then we specify family, binomial. Actually, yeah, and that's all you need for the default. The default for the binomial is the logit. If you want to specify a link function other than the default, such as probit, you also have to include in parentheses link equals, and then that alternative link function. All right, so let's look at an example that I really love because it demonstrates so beautifully a data set that follows a logistic sigmoidal curve. All right, so this data is from 1965 from Warsaw, Poland, where a couple of researchers asked a question of preteen or teenage girls whether they had experienced menarche or not. So menarche is the time when a girl has her first period, okay? As she starts her menses. And these, well, actually, I'm just going to scroll down and look at the data, and then we'll go back up. So here we've got the age of the girls, and these ages were actually broken into a bunch of different categories. We could have had their actual ages if we knew their birth dates. In fact, these age categories were certainly based on birth dates, but for a reason that I don't know, probably just for simplification, that this data can be summarized in 25 lines rather than having thousands of lines. We've got these categories. And most of the categories, for example, look at the 11s. These are basically quarter year increments. And then the 12s, there's 4, and 13s, there's 4. So most of them are quarter year increments. This first category is a year earlier than the next one, and this last age category is 2 years later as well. So these age numbers specify the midpoint of an interval that contains these ages. And for each age category, we've got the total number of girls. So look at we've got quite a large sample size here, several thousand. And then the number of girls in that group who had experienced menarche. So of those girls who are in the 9.21 age category, there were 376 girls. None of them had their first period, and so the estimated proportion of girls in the total population having had their first period by that time is 0. Then we continue, and we've got these different age categories. By the time you get up to about 13 years old, about half of the girls in those categories have had their first period. By the time you get up to about age 15, about 96%, and by the time you're 18, basically everyone at that point has had their period. So let me scroll back up for a moment, and we'll take a look at how this data came in. I'm actually pulling this data set from the mass package, and these are numeric values, but if I convert them to integers, they won't have decimal points for the total and the Menarche, which are integers. So this sort of just makes the data display a little cleaner. The one calculation I'm doing here is I'm calculating p hat, which is the observed proportion of girls in that age group having had Menarche. So we've got number with Menarche over the total. Pretty simple. All right. So let me scroll through all this text, and I'll come back in a second. On the left-hand side are p hat, those estimated proportions. So we've got the age group on the horizontal axis, and on the y-axis the estimated proportion, and you can see this beautiful sigmoidal S-curve. There's some deviations from that curve for sure. This point should actually be a little bit higher if it would follow the curve perfectly. Same thing for the group of points here. But largely, you know, except for that little bit of sampling error, this follows this model really nicely. All right, I'm going to scroll up and then we'll come back and look at this plot on the right. So we just looked at that lazy S sigmoidal function. And so now we need to think about modeling the data on the scale that we're going to model it on, which is on the Logit scale. So we're going to use this Logit link function, which takes the proportions or the probability of success and takes the log of the odds. And so the Logit is just a name given to the log of the odds. So P is the probability of success, 1 minus P is the probability of failure. That ratio, probability of success over failure, is called the odds of success. And then we're going to take the natural log of the odds to get mu. And it's on that scale, the log of the odds, that where we'll do our analysis. If I page down for one moment, this empirical logit is related to the log of the odds, and you can see that this is nearly a straight line. So we're going to fit a straight line over here on the logit scale. So this logit transformation, however, is defined for most values of p, but not every value. If p equals 0, then we have 0 divided by 1, and log of 0, that's sort of negative infinity or undefined. If p equals 1, then we have 1 divided by 0, which is undefined. And so we're going to calculate something called the empirical logits, which gives us a way to just adds a little bit of a correction factor to help when we observe p hats, those observed proportions, as being zeros or ones. If I page up for a moment back to our table, we actually have some of those values. These first three cases have p hat equal to 0, and this last case has p hat equal to 1. So I'll page back down. So the empirical logits are defined by adding a small correction to both, basically to p hat. So we're going to add to p hat 1/2 divided by n. Now n here is the total sample size. Oh, sorry, my apologies. It's actually n is the sample size that the number of observations on which p hat is based. Let me look at this for a second. Total, yes. Okay. So if I page back up for a moment, n for this empirical logit for this first group is going to be based on 376. All right, I'll page back down. So we've got our observed hat, p hat, plus 1/2 divided by 376. So this is like 1 over 700 something. And that's a tiny, tiny correction, right? Enough that we can live with it. Okay. All right. So now we've got all of our empirical logits are defined. And so here I'm going to calculate the log of, and I've done something here with my parentheses to sort of make this a little easier for me to read. I've got this first fraction, which is p hat plus that correction factor, 1/2 divided by the total, divided by, so that's success probability, divided by 1 minus that success probability with the empirical logit factor, and then taking the natural log. So I'm going to call that empirical.logit, and that is the second plot over here, the empirical logits. 0 here is when the probability equals 1/2. So we basically have a straight line, and we're going to do sort of straight line modeling on this logit scale, which is a nice feature of logistic regression because it's something we're familiar with. We're familiar with fitting straight lines or even quadratic lines. In fact, if you look at this first point and this last point, they're sort of unusual, right? If we were to remove those 2 points from this data set, we might actually think that we could fit a quadratic to this. You can see the slight curve. But just for the point, for this example in this chapter, we're just going to try to fit a straight line and see what happens. So that brings us to the simple logistic regression model. So we've got the log of the odds as our response variable, and we're going to fit that with a multiple regression model. In this case, we're going to start off with a simple linear regression, beta naught plus beta 1 x, and then we're going to estimate beta 1 and beta naught, and that will be our relationship. If I page up for a moment, basically we're going to fit a straight line to these data, and then we need to back convert that straight line on the empirical logit scale to an S curve on the probability scale. I'll page back down. So fun, depending on your definition of fun, exercise is to solve for P. So once we've estimated our betas, we want to estimate P from that. So if you solve for P, you'll actually get this equation here. E, the natural exponent raised to the right-hand side power, beta naught plus beta 1x, divided by 1 plus that same quantity. And that is our estimate for P. One way that I remember where to put the minus sign and where to put the plus sign is that logarithms tend to make numbers smaller, and so does a minus sign. So those are put together, whereas exponents tend to make numbers larger, so the plus sign goes with that. Otherwise, you can see a sort of similar structure here, right? We got a ratio with a function, and here we have a ratio with this function. All right. Got some text here. Go ahead and read through. This is about discussing odds of success and interpreting these quantities. Here's an example of what these relationships will look like. If I have a zero slope, okay, say that beta 1 is not significant, and so that, say, Menarche wasn't related to age, then you get a horizontal line. And that corresponds to a horizontal line on the probability scale. So we've got the log odds, this is the logit scale, and this is the probability scale. And those correspond. Basically, there's no relationship. The probability doesn't depend on x, and it's just a straight line with an intercept. If you have a positive slope on the logit scale, then you'll have a positively sloped S-curve on the probabilities. On the probability scale. And if you have a negative slope on the logit scale, same thing. You'll have a decreasing S-curve on the probability scale. Which means that when you interpret these beta 1s, that slope parameter, positive slope indicates that as the x variable increases, the probability also increases. So there's a nice relationship there. It's common to aggregate data so that for a given value of x, we might have multiple observations, as we did in the Menarche case. So we've got like 300 something for that first category, and we have some number of successes. But the raw data on individual cases are just going to be ones and zeros. So for every individual, you can break this first row up. In fact, let me scroll up for a moment to the original data. This first row can be broken into 376 rows, one for every observation. So you could have 376 ages of 9.21, and for each of those rows, you'll have a total of one person, and then a 0 for every one of them. That indicates that person 1 is a 0, person 2 is a 0, person 3 is a 0, all the way down to person 376, who's a 0. And so the raw data here has thousands of observations. So that's why we sometimes aggregate when we have multiple observations with the same covariate combinations. Page back down, find where I was. All right. All right. So let's think of how to first estimate beta 0 and beta 1 in a naive way, some way that we already know. And then we'll identify a problem with this, and I'll show you the correct way. Okay, so this is not how you would actually do this, but you very well could. If I page up for a moment, we've got this on the empirical Logit scale. We basically have a straight line, and we know how to fit straight lines, right? You can use multiple regression and fit this line. So I'll page back down, and that's what I do here. I actually use the LM function, which assumes normality of the residuals. Okay, that will actually be an issue here. And I can fit the intercept and slope, and from that get my fitted equation for the log odds, and I can solve that for the probability P. So for any given age, I just plug that age in, numerator and denominator, and that will give me the probability of having experienced menarche by that age. Okay, but the problem is, in that case, we're assuming that the residuals are normal and all these other things, but that's not the case. In fact, in most cases, if I scroll back up for a moment, data won't always look this nice. This data looks beautiful in this curve because I've got large sample sizes in every age class. You know, at least sort of 60 or 70 in every age class. And yeah, 88 is the smallest sample size here. So we have tons of data. In most cases, we'll just have sort of one or two observations in each for every combination of my covariates. And so in that case, if I have only, say, one observation, it's the outcome variable is either success or failure, so that's going to be 0 or 1, which means my p-hats are going to be 0s and 1s. If it's going to be 1 divided by 1 or 0 divided by 1. Even when this total number would, if it was if it was equal to 2, then the only possible number of outcomes could be 0, 1, or 2. So my p-hats are going to be 0, a half, or 1. So with that super coarse resolution, when you start looking at plots like this, you have points down here at 0, a bunch of those, and you have points up here at 1s. You have lots of those. And that's it. And so then you're trying to model a curve to that. So, and that affects what your logits look like as well. So we need a better structure that doesn't assume normality of the residuals. And if I keep scrolling down, we'll get to maximum likelihood estimation. So here we have a likelihood function which follows a model. In this case, we have a model which assumes a binomial distribution, which is what we have for each individual. We have the probability of success, which is what we're modeling. So imagine a coin flip where you have a variable probability of getting ahead depending on covariates, say the age of the coin, which is ridiculous. In fact, it's almost impossible to make an unfair coin, it turns out, as an aside. So we need a model, a likelihood model, that correctly uses the binomial distribution as its reference distribution for the random sampling that we're doing. And so that brings us to maximum likelihood estimation. And there's several ways to maximize the likelihood. So what does that mean, maximum likelihood? We actually want to find values of the parameter. So in this case, we're estimating the parameter p. We're estimating the value of the parameter p that makes the data observed most likely under that model. So we're finding a model that makes the data most likely. And p depends on these values beta naught and beta 1. So we estimate beta naught and beta 1 to give us probabilities p to make the data the most likely. There's some values of betas that do a bad job, right? If we had a decreasing relationship with age, that doesn't follow the increasing relationship that we observe. So that would be a poor fit. So we want to find an increasing relationship with age and the correct intercept to give us the most data that could potentially come from this model. And so one way to check whether our data are wise and our predictions, basically the PIs are the probability of success, n is the number we observed. So if you multiply n times p, the total number times the probability of success, that's going to give us an estimate of the number that we would have observed in a certain category. So if our prediction, n times p, is close to what we observed, yi, then this ratio is going to be close to 1. And if we take the logarithm of 1, that equals 0. And so this whole term would be close to 0. Okay. Similarly, everywhere I've got a y, I'm basically replacing it with np for the predicted value. So here the number of failures and the predicted number of failures, if those are close, then the log of that ratio that equals 1 is going to be close to 0. And so this whole term will be close to 0. And if that's true for every category from 1 to m, so in the Menarche example, I've got something like 25 categories, then this deviance d is going to be something small. And so we will actually want to minimize the deviance function, basically by finding values of pi, which depend on beta naught and beta 1. Those are the values we're actually solving for, that minimize this deviance d. And that, by minimizing the deviance d, we maximize the likelihood function, where we make the data, we find the model that the data is most likely to have come from. All right. When do we do a bad job? So say we have a model that doesn't fit the data well, then n times p is not going to be close to y. And when this ratio is far from 1, then this logarithm can grow big, either in the negative direction or the positive direction. And same thing over here. And so as those deviances get large, then we're not really fitting the data well. So we will have a test in a moment that asks whether the deviance function is small. And if the deviance function gets too large, that is evidence of model lack of fit. All right. So that's pretty much what a lot of this stuff says. The only thing that I've changed is I've got a p tilde, which is our empirical logits, or our estimates under the model. And the deviance has a chi-square distribution with m, which is the number of categories, minus r, which is the number of parameters in the model, number of regression coefficients. And so we can do a hypothesis test of whether the model seems to fit the data. All right, so let's fit the logistic regression model to the Menarche data set. So I've got some comments here. Go ahead and read those. There's a few ways to do this in R, but this is the way I prefer to do it. So here's my general linear model. The left-hand, notice there's a left-hand side of the formula, tilde, and then age. And the left-hand side is actually sort of compound. There's two values here. I've got a column, so I'm column binding the Menarche column. So that's the number of successes. And then the total minus Menarche is the number of failures. So I've got two columns, success and failure. And together, R knows that if you add them together, you get the total sample size. So we want to model the probability of success versus failure relative to age. We're going to use the binomial family, and Menarche is the data set that the values are coming from. All right, so I'm going to put that into glm.m.a, m for Menarche as the response variable, a for age, the predictor variable. And now we're going to look at some of the values that come from here, and we're going to generate some plots. So first thing is, in the data set itself, Menarche, I'm going to add a bunch of columns. For one, I'm going to add the fitted values. These fitted values are on the logistic scale, I believe. We'll see that in a moment. I'm also going to make predictions, which will show what the model thinks the values should be for each of the observed values of age. So I'm going to predict using the model that I just fit up here, the GLM model. And I want to, this is the data that I'm predicting for. So I'm going to predict for all the ages. I'm going to use the link function. And you just have to type that in. And I'm also going to grab the standard errors. That's going to allow me to get prediction bands for my regression line. So I'm going to put that into an object called pred, and I'm going to pull out the fit and the standard errors and put that as columns in the original data set. Then I'm also going to calculate the confidence intervals on the probability scale for every age. So I'm going to put in the fitted values. So fit here is going to be on the probability scale, something like 0.5, 0.8, numbers like that. And I'm going to add to that plus or minus 2 standard deviations, or 1.96. 1.96 comes from the normal distribution. Recall that 1.96 standard deviations from 0, or the mean, gives you a 95% confidence interval. So I'm going to subtract that for the lower bound, and I'm going to add that amount for the upper bound. So I've got fit of the probability divided by 1 minus e to the probability, and I've got plus or minus those bounds. All right, oops, I pressed page down. I meant to scroll down. So let's look at one example. So here's, let me get a little more on the screen. Here's row 21. These are girls aged 15, roughly. I had 122 girls with 117 having experienced Menarche, and so my estimated or observed proportion was roughly 0.96. I think I have that value. Let's see, is this? Okay, that's fine. On the Logit scale, the estimated value is 3.06. That's the empirical Logit scale. So that's converting p hat to the Logit scale. Then I've got my fitted value from here to the right is from the regression model. I have a fitted value of 0.97, which is close to what we observed. Okay, It's actually a little closer than the rounding error gives off here. The fit on the empirical Logit scale, or on the Logit scale, is 3.38, which is pretty close to 3. The standard error of that fit is 0.14, so we're sort of within about 2 standard errors. And then here are the lower, unfortunately on the right, and upper on the left, bounds for the fitted probability scale. So here is, I think, the 6. The way I've written this, I actually don't. This must be the fitted value. So 0.967 is the predicted value for these girls, and with a confidence interval 0.958 up to 0.975. So actually a pretty narrow confidence interval. By the way, these confidence intervals do not need to be symmetric, and often will not be when you're close to 0 or 1 in probability. Here's the whole table. And it's from this table that we can plot the data, which are the p-hats, and then plot the fitted values and their confidence interval. So here's the summary of the linear model. And so we've got the intercept of -21. We have an age of 1.6. And these are actually pretty tricky to interpret because we care about things on the probability scale, not on the Logit scale. Logit scale is a little hard to interpret. But what is clear here is that the age is positive, which says that as you get older, your probability of having experienced menarche increases. From this output, we also have the residual deviance and the degrees of freedom, which will allow us to do a goodness of fit test to see whether that deviance number is small, which means that we don't have evidence that the model doesn't fit the data, or if the deviance gets large, it suggests that the model does not fit the data. We also have an AIC, which would be useful if we were doing model comparisons. So let's take a look at maybe one more comment here, which this reminded me of. The iterations, there is not a closed form for solving for the beta coefficients, these numbers here, in a logistic regression. Instead, these numbers are solved for using a maximization routine. And so that maximization routine in this case is called something called Fisher scoring, which is something I teach in my statistical computing class. And it took 4 iterations. Basically, it starts at some guess value for these beta values, and then it iterates, and each iteration brings you closer and closer to the best beta values. And after 4 iterations, you got close enough to say, well, I can't really improve substantially on my estimates, so I'm going to keep those. All right. Finally, let's test whether our model seems to fit the data using the deviance statistic. So I've got the deviance statistic of 26.7 with 23 degrees of freedom, and those we read right off of here for the residual deviance. And we can pull those numbers out from the linear model using deviance, that's this number, 26, and the degrees of freedom, df residual, 23. And because we follow a chi-square distribution, the p chi-square function using a deviance statistic of 26 and degrees of freedom of 23 gives us the left tail from a chi-square. So chi-square, I'm waving my hands now. A chi-square distribution is, if this is the axis, is a right-skewed distribution. And on that right-skewed distribution, this is going to give us the probability of observing something less than or equal to that value. And so 1 minus that is going to tell us what the right tail probability is. That's the p-value. So I'm going to assign that to p-value, and we get, in this case, about 1/4. So that's a large p-value. We don't have strong evidence here that the model does not fit the data. And a typical rule of thumb here is not to use 0.05, but to use 0.1 as a cutoff. And unfortunately, this is largely the only way we have of assessing the fit of the regression model. I guess there are a few other things we can do if I page up for a moment. From those betas, we could actually plot on the empirical logit scale a straight line. If those empirical logits are nice the way these are, where we've lots of observations, typically the empirical logits are going to be 0 or 1. Or rather, the probabilities are, and then the empirical logits are going to be two values that are sort of extreme. So it's really hard, unless you've got data as nice as this, to see whether a straight line is a sensible model for the data. All right, paging way back down. All right, so some comments. The maximum likelihood estimates, which are the correct ones that we should use, are actually fairly close in this case to least squares, but in general that may not be the case. And if we plug those regression coefficients in to our model, this is our fitted model, and this is then the model we used in the table above to make those predictions. We plugged in age, and we solved for this and solved for p. So now I'm going to plot that, and we'll go back in a moment and look at the plotting code. So the black dots are the points that we observed. That was from the plot before. The red dots are the model prediction, and I've connected that with a red line because those predictions apply even for values of x for age that we didn't observe. And then I have a gray line, or a gray bar, which is the confidence band around the regression line. So with 95% confidence, we with 95% confidence, we are 95% confident that the true regression line, at least point-wise, falls inside that gray regression band. All right, so let me scroll up for a moment, and I'll show you how I created that plot. So I'm going to start off just by plotting the age as the x-axis and p hat as the y-axis. The ribbon function is one way to get a confidence band. It basically plots from a lower bound to an upper bound over a range x. So for each value of x, I've got a minimum, the fit lower, and the fit upper maximum, and it's going to plot that gray bar. And it starts off as black, but I set it alpha to 0.2 so to make it gray. Then I'm going to connect the dots for the fitted values, and I'm going to color them red, so that gives me the red line. Then I plot the red fitted values points as red, so those give me the red dots. And then finally, the geom points plots the black points. So you can see the black points lay on top of the red. And then I just give it this long title. And notice I've got a /n here, which gives me a new line. So I've got 2 lines of text in the title. All right, we're coming to the end here. I don't think there's that much more to say. We can test, as we've done previously, I think maybe in chapter 7, multiple terms if we needed to, using the Wald test. And I think we may do this in a later example. So from the AOD example, we can use this generalized linear model object, and we can test, in this case it's not very interesting, just the term, whether term 2 equaled 0 or not. So we can use the Wald test, put in the coefficients, put in the variance covariance matrix as sigma, and then ask whether these terms are all equal to 0. And here I'm doing the range of terms 2 up to 2, so the second term, whether that's equal to 0 or not. and our test statistic is very large, and our p-value is basically 0. So there's strong evidence to say that this term is different from 0. And that's, of course, the same conclusion we had by page up here when we looked at the summary of that generalized linear model object. All right, so we'll come back and we'll look at an interesting example with leukemia, where now we'll have a second covariate which indicates a disease status.